Hi everyone, welcome back to my channel. My name is Omid Jazi. I'm an assistant professor of statistics. This is the second lesson for a short course on longitudinal data analysis. In the first lesson, we learn what longitudinal data are. They are basically repeated observations of the same subjects over time. In the second lesson, I'm going to talk about exploratory data analysis, how to understand the data before we fit a model and do a statistical inference. So, what is exploratory data analysis or EDA and why it matters? EDA is the process of learning from data, spotting patterns, visualizing trends, and identifying potential problems early. It helps bridge raw data and modeling. And before we ever fit a model, we want to know if there is any patterns, there are any outliers, and how variables change over time. So for our example, let's generate some longitudinal data. Let's say we have a student test scores. We have 10 students. We divide them into two groups of 5 control treatment groups at 5 time points, and those test scores represent students' performance. And this simple setup gives us both repeated measures as well as group comparison, which is a classic longitudinal data structure. So let's start with basic summaries, means, and standard deviations at each time point for each group, which helps us understand whether or not scores are improving over time, and if the treatment group behaves differently from the control group. For example, we might find that both groups improve over time, but the treatment group improves faster. Next, we have a spaghetti plot, which is one of the most powerful tools for longitudinal data analysis. Each line represents a student trajectory over time, and when those lines are roughly parallel, it means that the consistent growth patterns across those students. But if lines across or spread out, it means that there's a lot of variations and maybe some students improve faster than others. Next, we have group means plot. So we plot the group means scores over time, which simplifies the spaghetti plot and shows a clean comparison between the two groups. For example, we notice the treatment group starts slightly higher and it rises faster, which is a hint for our future models that, for example, we include the group by time intersections. Next, we have scatter plots between early and later time points, which helps visualize within subject correlation. If subjects who start high tend to stay high, we will have a strong upward trend. But if points are more scattered, it suggests less consistent performance over time, which is a weaker correlation. We can confirm these patterns by a correlation matrix for repeated measures. Usually measurements that are closer in time, let's say time 1 versus time 2, have darker colors, which shows there is stronger correlations than those farther apart, let's say time 1 versus time 5. This declining correlation over time is one of the defining feature of longitudinal data and has direct implication for our model choice. EDA is also the stage to spot unusual subjects and missing values. For example, at time 5, we have an outlier for the control group. One student has a very high score, and missing values are quite common in longitudinal data. We will discuss in future lessons. So, in summary, EDA helps us understand patterns in means and variances over time. It helps visualize subjects and groups trends over time. Also, we can identify within subjects correlation, and finally, we can detect outliers and missing values. In the next lesson, I'll talk about linear regression models for longitudinal data. Thanks for watching. If you found this helpful, please subscribe for more lessons on longitudinal data analysis. See you next time.